so that we can use it to solve recurrences. And you may have seen different ways of solving recurrences even before generating functions. You may have seen what is called the master method, right. You want to solve a divide and conquer recurrence, then you have this master method which gives you a formula for different cases, right. So, Tn is a Tn by b plus some function, right. You may have seen this is also a recurrence, right. This is saying this term, the nth term of some sequence depends on so many repetitions of the n by bth term in the recurrence. A typical divide and conquer recurrence, right. To compute something, your algorithm on n steps has to run something a times a smaller problem on n by b of size n by b. Okay. So, you may have seen that if using some properties of this function and so on, you can give a closed form expression, you can solve this recurrence also. So, but that approach, master method and so on, will not apply in this case, right. It will not work in this case, the settings do not work. So, generating functions is a very powerful tool that can help you not only solve recurrences, it can help you also come up with recurrences, right, maybe invent recurrences. Right. So, why would you want to invent a recurrence? Okay, so what are we trying to do? So, we are trying to study a sequence, right. So, sequence, right. So, sequence of numbers a0, a1, blah blah blah, and we want to understand some properties of this sequence, right. So, Fibonacci numbers, Fibonacci sequence is one such sequence, right. You may have other sequences, the sequence of prime numbers, for example, right. So, we want to study properties of such a sequence, and generating functions is one way of studying that. And application that we will see is you can solve a recurrence, whatever that means, you can invent new recurrences. Why would you want to invent a recurrence? So, if somebody were to ask you compute the nth Fibonacci number, would you use this formula or would you use this formula? Second one. Why?
It seems like a more direct way to get the answer.
But you want to work with square root 5? Do you really want to work with square root 5?
If I had a calculator.
Okay, but will you do it if you start working with this? Well, you have to worry about approximations. I mean, clearly this is not the correct answer because you will have a square root 5 sticking out. So, you may try, but if you have a more algorithmic or computational mindset, you will really go for this one, right. You will do your recurrence, you will set up your stacks, compute it in order n time, right. To compute the nth Fibonacci number, you can use this recurrence to come up with an algorithm. If you store use your memory carefully, then it will be a polynomial, not even polynomial time, a linear time algorithm, right. So, recurrences are much more useful if you want to compute terms. Okay. So, you may want to invent recurrences. Not only that, you may want to study the numbers itself. So, the asymptotics. Can you see what I am writing? Is it legible? So, like how large is this number? Is this order of n? Is this order of 2 raised to n? Is this order of square root n raised to n? Or maybe theta of these, right. So, what is asymptotics? You want to study the growth of your numbers, the behavior of your numbers when they grow, as you go larger and larger in the sequence, right. So, for example, you may have that you have these two sequences, which of these two sequences is larger. So, you may say, oh, is this larger or is this larger? So, if you know the asymptotics, the behavior of the sequence far away for large values of n, then you can try to answer these questions. Okay. For example, you can define your sequence to be this is again 2n choose n. Okay, you know what 2n choose n is. You have a formula for 2n choose n. Can you come up with a recurrence for 2n choose n? Right? Can you come up with how large is 2n choose n? Right? So, generating functions can help us answer these questions. Okay. So, what is a generating function? So, it's a so you can read up this book. This is a beautiful book by Herbert Wilf called Generating Functionology. Okay, so the science of generating functions in some sense. It's a very beautiful book, easily accessible. You can read it up. So, what Wilf describes a generating function is, okay, so you have these numbers, this is given as a discrete sequence A0, A1, A2, so on. So, it is like a clothesline where you are tying up all these numbers and you see them in one shot. Okay. So, how do we tie them up together? So, he says, so one way to tie them up is you define a function as associated with the sequence as follows. So, it is just, so introduce a variable and consider this sequence. Okay, so introduce a variable x and treat, you have this, you associate a function, it is called a power series. Okay, such an expression is called a power series. So, associate a power series with your sequence. Okay. So, now we have tied them all together. Do we understand the definition? Is the definition clear? Right. So, let us do an example. So, what is the, so if the sequence is just the sequence of all ones, right, what is the generating function associated with the sequence? Right, so, it is just a n is all they are all ones. So, n summation of x raised to n greater than or equal to 0. Yeah, so what is this sequence? You take it outside, yeah. So, this is the generating function that we will associate with this sequence, okay, and the sum of x raised to n greater than or equal to 0, and is there a succinct way of writing this sequence? Yeah, okay. So, we say this is equal to 1 by 1 minus x if mod of x is less than or equal to 1, that is what we usually say, right. But I will drop this thing, okay. Why, it will become clear later. We will not say this, we will not worry about that constraint. Why do we have to worry about that constraint? I mean, why do we say, well, this is equal to this if the absolute value of x is less than 1? We thought about that. Why do we have this? Huh? For, yeah, so convergence, right. So, when are we worried about convergence? When we are going to evaluate this function at a certain choice of x, right. If I try to evaluate it only at x is equal to 1, is there real trouble? Otherwise, Okay, for x greater than 1, this side is not converging maybe, but this is well defined. But for x less than 1, if you evaluate these two sequences, you get the same number, right. So, if we want to evaluate this sequence, this function, then we have to worry about these things, but if we do not, if we just multiply 1 minus x with the summation, what will we get? Right, let us do that. So, this is 1 is just giving us x raised to n, and then x will be multiplied. So, that will be n greater than equal to 1, right, and what we will get is 1. Okay. So, what this is really saying is this function multiplied with this function is 1, that is all this is saying. Okay, we will never evaluate this function at any point. Okay, what we, when we say this is equal to this, we mean it in that sense. Okay, or when we say that two generating functions f of x, two functions are equal. So, this is, let us say, summation of a n, this is summation of b n. So, this is if and only if, these two are equal coefficients, right. Okay, if you take all the coefficients, they are same. So, basically they are the same generating function. Okay. So, we will do this in more detail in the next lecture maybe, but for now the only thing that you have to keep in mind is, okay, so for the sequence we have this generating function, and we will never evaluate this function at any point. We will only play around with that function, in this sense, multiplying two such functions, adding two such functions, okay, basically only these two kind of operations. So, what is called we will do addition, subtraction, multiplication. Okay. This is fine. Any questions? Okay. So, let us take our favorite recurrence. So, so this is the most fundamental generating function, if you have to remember. Everything else follows from this. Okay. And instead of this, if you have alpha raised to n, okay, alpha is some constant, say alpha raised to n. So, the nth term is just some constant raised to n, then the generating function will be what? Maybe let me write it there. Right. So, the generating function is, which is, what will be that? We taking q from this, 1 minus alpha x, right. Right, you just substitute y is equal to alpha x, you will get summation of y raised to n is 1 upon 1 minus y. So, 1 upon 1 minus alpha x, the same argument, this argument goes through. Okay. So, these two are our fundamental generating functions. Okay. So, geometric series, basic geometric series, right. Okay. So, let us start with that. So, let us define f of x to be the generating function for the Fibonacci sequence, right, which is what? F0 is 0. So, this is F1 is 1. So, this is x plus F2 x square, so right. So, this is by definition we are saying that this is the generating function for the Fibonacci recurrence or the Fibonacci sequence. Okay. Now, somehow from there we want to derive some such formula for the nth Fibonacci number. Okay. And what we are given is this. Okay. So, this is saying something about the numbers. We want to use this to say something about the generating function. Okay. So, what do we do? Just blindly multiply this by x raised to n and sum it for all n. Okay. So, if I multiply that side now, we are multiplying by x raised to n and tying the clothesline, right. So, by summing up we are getting this. Sorry, I can't do n greater than equal to 0, I have to do, because there is an n minus 1, we have to do n greater than equal to 1. Is this fine? Right, from the recurrence we can derive by doing this multiplication by x raised to n, summing it up for certain choice of n, a valid choice of n, we are getting something about, hopefully get something about the generating functions. Okay. Okay, so, not seeing the sequence individually, but all at the same time. Okay, so, let us see what is this sequence. So, now our goal is to express all these terms in terms of this. Okay. Let us start with this. What is this sum? Hmm? Well, let us see what is this. This is n is equal to 1. This is just what? So, f1 x. So, f1 is 1 plus f2 x square plus f3 x cube. It is exactly the same sequence, right. So, let me just write f for that. What about this side? So, this is f0, which is 0, f0 x plus f1 x square plus f2 x cube, right. What is this sequence? X times f, and what is this? This is f2 x plus f3. So, this is lagging behind the index, right. So, what is this sequence? F starting f2, right. So, you have to remove this. So, f minus x divided by x, right. So, okay, so we have that this quantity is equal to f plus x times f. Okay. So, all the sums have disappeared. We have this an expression which is in terms of this series and x, right. So, in some sense we have got a recurrence for our generating function, right, but it is independent of n now, n has gone, it is out of the window, right. So, now we can manipulate the terms and solve for f. What will we get? F minus x is x times f plus x square f. So, f is x upon, so move this side, okay. So, we have a closed form expression for f, right, that this is equal to x upon 1 minus x minus x square. Is the derivation okay? Do we follow the derivation? It's just algebraic manipulation, right? Right? If anything is hard, why did people invent algebra? Huh? Why did people invent algebra, or what is the difference between art and science? It's a very broad question, I know. Right? So, algebra we can do it blindly, right? You can write an algorithm. You don't have to be creative in doing these things, right? You can just write an algorithm which will manipulate the symbols and it will give you the answer. That's the beauty of algebra. It's a manipulation of symbols, right? You may want to interpret them, you may want to understand the semantics behind the symbols, but at least in terms of manipulation, which we are so proud of, in our school days we have done all that manipulations, right? So, this is just doing that kind of manipulation, and you can in fact write an algorithm which does this for you, right. So, Don Knuth, he says, right, what is the difference between art and science, right? Science is art dumbed down, okay. Science is art that anyone can do, right, by using the necessary tools and techniques or algorithms. If you can devise an algorithm to do something, then anyone can do that. We all use Google, we did not come up with the algorithm for using Google, right, or doing the search. So, that is where the difference between science and art comes, right. Art we can't, you have to be really creative to do art. Science we can pull off by doing something like this, or at least some part of science, okay. So, now we still do not have this, right. We are trying to get a formula for the nth Fibonacci number. What you have got is a closed form expression for the generating function for the Fibonacci sequence. So, how do you go from there to this? So, what we will do is, let us see this, okay, let us see 1 minus or x square minus x square plus x, right. So, what are the roots of this equation? So, we want to write it as x minus something and x minus something, right. It is a quadratic equation, it has two roots, right. So, what are the roots? Let us say a is what, so minus 1 minus b plus b square minus 4ac, so 5 by 2, and it's somewhere the golden ratio has to come in. Is this fine? So, this would be if we factor this polynomial in terms of this, okay. But what we really want to do is, we want to write not in this form, we want to write this as some number upon, because we know this expression, okay. So, instead of factoring it like this, we really want to factor it as say a times, not a, so let us say phi plus times x minus 1 into phi minus x minus 1. So, we know that this x square plus x minus 1 is equal to x minus a into x minus b, a and b are this, but we really want to write it not here, the constant should not be there, but here there is. Okay. So, we want to write it in this form, and so how do you get from this factorization to this factorization? So, we want to find two numbers phi plus and phi minus such that their product phi plus times phi minus is 1, their sum is the sum of a plus b, and so if you try to solve for these, what we will get is phi plus is what we really want and phi minus is okay. So, we can check that these two numbers would do this job. Okay. You can try to solve it as well, you can check this. So, do we understand what we have done? So, we have factored this degree 2 polynomial into two linear factors, okay, but not in the familiar way, in this slightly different way. Okay. So, how would you do this? You would pull out a, you will write it as ax minus 1, ax by a minus 1 and b x by b, right. So, from this you can figure out what is phi plus and phi minus. Given a and b is this, you can solve for phi plus and phi minus. Okay, roughly phi plus is 1 by a, phi minus is 1 by b, or other way around. Okay. So, the reason is we want to write this ratio of these two polynomials in terms of two numbers c and d and these linear factors. So, this is called the partial fraction decomposition, right. So, we want to write this ratio of two polynomials as a sum of ratio of degree 1 polynomials, right. So, partial fraction decomposition. And fractional decomposition. Why would we want to do that? Because we understand this series 1 upon 1 minus phi plus x is just this phi plus raised to n x raised to n, 1 minus phi minus will be again phi minus raised to n x raised to n, right. So, we understand these geometric series. So, if we now wanted a formula for the nth Fibonacci number, the formula would simply be by equating, so the coefficients on both sides. So, this is summation of f n x raised to n. Okay, so, the left side we have the Fibonacci number, the nth Fibonacci number, the right side is using this fact, it is c times phi plus raised to n minus or plus e times phi minus this. Okay. So, if we knew c and d, we have our formula for the nth Fibonacci number. Do we understand how we went from from the generating function? This is the generating function. We write the generating function into the simpler generating functions, some of these simpler generating functions. The coefficients of these generating functions we understand because of this. Okay, and then we just equate the coefficients of x raised to n on both sides. Right, we just do this. Okay, these two are the same generating function, so their coefficients must be the same. Left hand side is the Fibonacci number, right hand side is this thing. So, if d was 0, we will be in this thing, but the question is what is c and d? How do you solve for c and d from this? Yeah, so you can multiply and solve for it, right. So, what should this be? So, c times this plus d times this should be x, right. We just do that. C times, so x is what? C times 1 minus phi minus x plus d times 1 minus phi plus x. Since there is no constant term here, C should be equal to minus d. So, this is, and what is this? So, C is equal to minus d, and 1 is equal to d times what, phi minus, so this is phi plus minus phi minus this. Okay. So, d is 1 upon, let us say, phi minus, and C is 1 upon. Okay. So, the difference between these two numbers. Okay, so, that is C and D. So, what we get is, this is 1 upon phi plus minus phi minus into phi plus raised to 12 minus phi minus raised to 12. Okay. This is the formula for the nth Fibonacci number. Okay. Not this one now. So, you see there is the golden ratio. This is 1 upon square root 5. So, this is the formula. So, the idea is you are given the recurrence, you come up with the generating function, you solve for the generating function using properties of the generating function like this, you can come up with a closed form expression for your number sequence. So, asymptotically this is true. Asymptotically means for large enough n, for large enough n, this quantity phi minus is less than 1, this will go to 0, phi plus is greater than 1, this will go up. So, for large enough n, this is right, this is the dominating term, but it is not equal to, it is approximated by. Okay. So, this is saying asymptotically this is maybe, okay, this is order of this, not exactly equal. So, do we understand the, the overall idea of coming up? So, given a recurrence, you can come up with a generating function and you can come up with a closed form expression. Okay. So, let us do some more examples, something more familiar. So, let f and k be what okay. So, be the number of k size subsets of an element of a universe of size n. Right. How many subsets of size k are there of a subset of a set of size n? We all know the formula, right? What is it? n choose k, right. But I mean, if we do not know the formula, let us say we only knew that this is the definition of your sequence. Okay. How can we come up with the formula? One is to do this combinatorial way that we are all familiar with. The other is, okay, let us start with a, can you come up with a recurrence for this number, right. Come up with a recurrence, apply this, put on your generating function hat, hit it with x raised to n or x raised to k, sum it up, find the generating function, find the coefficient in the generating function. These are 3 steps. Okay. First, come up with a recurrence, or you may have already a recurrence, then do this summation thing, right. Then solve for the recurrence. Once you have this recurrence, simplify the recurrence to get a new way of writing the recurrence like we did here, and you may have a closed form expression for your sequence. Okay. So, this is a cure for all your remedies with recurrences. So, what is the recurrence for this number? I mean, there are many recurrences. The one that we are most familiar with. Right. How can we form a k size subset of a set of size n? Yeah, so let us fix one element, right. Let us say we fix the last element, right. Either that is part of your subset of size k or not part of your subset, right. That is, there are only 2 possibilities for a subset, right. Either it contains the last element or it does not contain the last element, right. How many possibilities are there if it contains the last element? Right. So, your set S has 2 forms, either n is in S or n is not in S, right. So, if n is in your set of size k, then how many possibilities are there? N minus 1 k minus 1, right. F of n minus 1 k minus 1, right. So, the remaining, from the remaining n minus 1, pick the remaining k minus 1, or from the remaining n minus 1 pick k, right. That is the recurrence that we know. Okay. Okay. So, we have a recurrence, that is a step 1. Now, we define our genetic function, right. So, let us define Bn x, the genetic function corresponding to this sequence, sum over all k, Fn k, x raised to k. Okay. So, the closed line, we have tied this sequence. Is this an infinite sequence?
N and K are finite.
Yeah, n and k are finite. Well, it is not clear. Well, n is some large enough thing, we do not know, n is some number, but as k goes beyond n, this will be 0. You can't have subsets of size larger than n, so this will be 0 after some time, right. So, in fact, this is a polynomial. It will stop at k is equal to n, it is a polynomial. This was not a polynomial. This was an infinite, this was really an infinite sequence, it was not a polynomial, it was a ratio of 2 polynomials. Yeah. In fact, you know what the polynomial is, right. If instead of f and k we had written n choose k, what would this be? Right, you know this, we had written it like this in a more familiar form, what would this polynomial be? x raised to n, 1 plus x raised to n, right? Yeah, binomial. So, you know the answer actually. Okay. So, what we will just do is we will follow the steps and see whether in fact we will come up with this or not. So, let us do that. So, we have a recurrence, we have defined our generating function. So, what do we do now? We take a recurrence, hit it with x raised to k on both sides. So, we take a recurrence, okay, multiply by x raised to k and sum over all k greater than or equal to what should we do? Let us say equal to 0, let us do it. Okay. So, this left hand side will be x raised to k is equal to x raised to k. Okay, you may have to worry about here, this is saying f n minus 1 minus 1, but let us say by definition if k is here less than 0, it is 0, right. You can define n choose k to be 0 if k is less than n, k is less than 0, right. Okay. Okay, note one difference here is there is an n here. Earlier when we did this, the n had disappeared completely, right. Why? Because there are two things to worry about here, there is n and k. In fact, you could have chosen the sum to be over n, and then it would be a function that depends on k. There are two choices, right. With foresight, let us say we chose k to be the variable, n is something we do not touch. So, what will we get here? We will get the left hand side is just by definition b n x. What is this? Well, if we pull out x here, now is it easier? b n minus 1, right, x times, right, because these two indices are the same, right. So, this is just instead of n we have n minus 1. So, this is, and what is this? b n minus 1 again, right. This is n minus 1 is fixed, summation is over k, right. That is how the definition is, whatever n is fixed, summation is over k. So, this is, and in fact this is common. So, we get this is okay. So, you open it up again by, so now you have a recurrence for the generating function b n is 1 plus x times b n minus 1, which will be 1 plus x times b n minus 2. So, if we keep continuing this, what will we get? b 0 x, right, b 0 x. What is b 0 x? Right, it is a generating function when n is 0, 1, right, 0 choose k is 0 except when k is equal to 0. So, this is 1. Okay, so, this is what we expected. You can say this is like holding your ear the other way around or nose the other way around, but that is always true for anything which is so powerful, right. In some cases it is an overkill. Okay. See, okay, still if you think formally, we still do not have a closed form expression for this number. It's only because you know that 1 plus x raised to n has coefficients which are n choose k, you can make that claim now that okay, Bn is, by comparing the coefficients, we know that, sorry, not Bn, Fn k is n choose k. At the last step, you have your generating function. On one side, the generating function is this, right? Coefficients are Fn k. On the right hand side, you know the coefficients are n choose k. So, you can say that this is the same number. Okay. So, we are writing the generating function in two different ways. When you write the same thing in two different ways, something nice comes out, right. So, that is what happens. If we have still not formally proved that the coefficient of the kth coefficient of this polynomial is n choose k, but I leave it to you, you can figure it out as an exercise. Okay. How do you prove that the coefficient of x raised to k in that power is n choose k? Okay. So, you can do that, it is not that hard. So, now we understand the steps, right. So, you are interested in some number sequence, okay. So, you want a closed form expression for that sequence. So, first is you are given some definition of that sequence, you come up with a recurrence, you hit it with this generating function, this is the crucial step, right. Hit it with some power, do this generating function business, manipulate the generating function, express the generating function in a different way, and then compare the two sides. The same generating function has two different expressions. So, the coefficients have to be the same, and voila, you will have that whatever you are interested in has a nice expression in terms of something else. Okay. Okay, let us continue this theme. Okay. So, let us define n curly k as the number of partitions now of a set of size n into k non-empty disjoint sets. Okay. So, we are writing n as S1 union. So, we do it like this usually, right. So, you write it as a disjoint union of k non-empty sets. In how many ways can we do this for this set M? Okay, let us say that is our number n curly k. Okay, for example, what is n curly 1? In how many ways can you partition a set of size 1 n into, yes, only one set, that set itself. So, this is 1, n curly 2,
n plus 1 C1,
for n curly 2.
like if we have n objects at least, then we need to find like one position. Oh yeah, NC, yeah, n.
Why 1? You can pick it, you are saying you are in that order only.
Yeah.
You can mix and match also, right?
Oh, okay.
Yeah.
Oh, we are considering that like the order also matters.
No, ordering does not matter, it is like so you understand, right? N curly 2 is the number of ways to partition a set of size n into two buckets which are not empty. You have n in n numbers you want to put it into two non-empty buckets. Okay, every number has to go into some bucket. In how many ways can we do that? Hmm? And what? Sorry? Sorry, what, one by one. What? That is saying just the size of set 2, no, right? You are not just putting two elements, you are breaking your set into two sets.
2 to the power n minus 2.
Plus more, yeah. 2 to the power?
N minus 2.
Okay, why is it 2 to the power n minus 2?
First you are putting 2 on 1. The rest has 2 options.
Each element chooses
No.
which bucket it goes in.
Each element, okay. 2 power n, okay. That is each element choosing which bucket. What is it? So isn't it like if some elements have chosen to go in the first bucket, what are we saying? Everything else has to go, the disjoint has to go into the other bucket, right? Okay, so 2 power n minus 1, right? Because you put the, you pick a subset and say it goes in the first bucket, then the complement of that subset has to go into the second bucket, right? Clearly they repeat because the complements you are counting them 2 times, right? So in one bucket A goes and then in the its complement goes in the other bucket. This would be 2 power n, but there is a over count because what if I had A complement here, then I will get the same partition, right. So, we are not worried about the ordering of the partitions. So, 2 power n minus 1, but no bucket can be empty, minus 1, right. We have already accounted for over counting. So, minus, right, empty, no, you can't pick the empty subset, right. For every subset of n, there is a over counting 2 times. So, that is minus 1, but you can't pick the empty subset. So, remove that, right, or we would have done this way, same thing. So, it is a huge number, it is already compared to n choose 2, this is right out of the window. Okay. So, in fact, these are called Stirling numbers of second kind. Which means there must be Stirling numbers of first kind also. But not worry about that today. Okay, so what we want to do is, okay, understand these numbers, right? Just as n choose k, we want to understand this sequence. What is the generating function for this sequence? And in fact, we want to study the more this number really, which is, so this is counting the number of partitions of n into exactly k non-empty right sets. Bn is called the Bell number, which is the number of partitions of n. Okay. Non-empty partitions, right, which is, once we have this, it is just let us throw in 0, it is easier. And this is called Bell number. So, this is named after Eric Temple Bell, who wrote this a very famous book on men in mathematics. it's controversial also. Yeah. So somehow using the generating function for these, hopefully we will be able to come up with a generating function for this, and what we will do is we will turn the tables and we will try to come up with a recurrence for these Bell numbers. Okay. So hopefully we will do that today. So let us start with this. So can we come up with a recurrence for the Stirling numbers? Right, that is the first step. If you want to get the generating function for a sequence, come up with a recurrence. Right. In fact, that is also, if somebody was to ask you, right, how do you compute these numbers? You come up with a recurrence. That is the first thing you do. So the hint is exactly, let's follow that idea, right? Let's try to follow this idea. Why is it not the same sequence? Right. So right. So what do we say? Is this equal to this? Would this make sense? Well, I mean, if it was equal to this, we will end up with the binomial numbers, right? Clearly, this cannot be true. So something is wrong with this claim, right? This is not correct. So remember what was, how did we get this? We said, okay, so a subset either has the last number or it doesn't have the last number. We want to do something similar here, right? So how can we reinterpret that and maybe correct it in the way? So you have to have k partitions, right? So either the last number is in its own partition, right? N is, so it's the only number in its partition, or N shares a partition. And these are the only two cases, right? Of the k partitions, either N is in a partition of its own, or N shares a partition with some other numbers, right? How many options are there for this? If it is in a partition on its own, this one, right? N minus 1, the remaining N minus 1 numbers have to be partitioned into k minus 1 partitions. And in this case, the remaining N minus 1 are partitioned into k partitions, and N is in one of them. So k times this, right? Exactly. Right, very good. So we have a recurrence. Okay. So now we have to define our generating function. Sorry, I have used two B's here. This is, let's say this is script B. So here when we define this generating function, we very judiciously chose to sum over k, right? As I said, we have two options to define. We can define just like that. We can define a n of x as sum over k of our sequence, or we can define as k of x as sum over n. Okay, you have two choices. Okay, you can work with both, and they will have their benefits and challenges. But let's say, let's for just change of taste, let us do this one, and it will become clear why this is slightly easier in this recurrence to work with. I mean the idea is same. If we multiply by x raised to n and sum over n, the one nice thing is the k comes out nicely, right. If we had done sum over k, then this k will cause us some problems, and what we will have to do is we will have to differentiate our recurrence or the genetic function to get that k out. Okay, if we do it in this way, then we kind of avoid differentiating our function and solving a differential equation. That is what it is. Okay, you can do that, it is absolutely fine, but let us not do that today. Okay, so let us work with this form. We fix k and vary over n, right. So what will we get? Right, this is again, this is our generating function itself, skx. What is this sum? Okay, remember this is how we are defining x. Sk is sum over n, okay, x raised to n. So here k minus 1 is fixed, right. This is not matching. We can pull out an x, then these two will match. K minus 1 is fixed, so we will get sk minus 1, x times x sk minus 1 x. And what is this? Again pull out x. Now we are, the index is same, that is varying. So this is kx times sk of x. Okay. So we have sk on the left, we have sk on the right. So we have the recurrence sk of x is x times sk minus 1 of x upon 1 minus k of x. Okay, it is slightly more involved than what we had for the binomial terms. Right, there it was just bn was 1 plus x times. Right, so it was nice. Here we have this ratio x 1 minus k. Is this fine? Is the derivation okay? So we can, so we have this recurrence for our generating function for the Stirling numbers. So if we open this up, this will be x upon 1 minus kx. This will be x upon 1 minus k minus 1 x. Okay, it is already getting pretty ugly. And when do we stop? Again S0 of x. So it will be x upon 1 minus x, S0 of x. S0 of x is k is 0, let us say it is 1 again, right. 0, only 0, curly 0 is 1, everything else is 0, right. So it is this. Yes. So it is pretty involved. So it is x raised to k upon the product of all these 1 minus kx, 1 minus k minus 1 x, all the way till 1 minus x. So not bad, at least we have an expression for the generating function. It's now how do we manipulate with this expression, right. So, remember this is like the one for that we had for the Fibonacci number, it was a ratio of two polynomials. So, when it is such a ratio, and here we already have this nice factorization in terms of linear factors, right. 1 minus kx, you know the coefficient of 1 upon 1 minus kx is k raised to n, 1 minus whatever cx is c raised to n, the power series. Okay. So, what we will do is we will try to write this, whatever this is. So, the partial fraction decomposition of this, right. So, a k upon 1 minus k. Okay, so we have to find these numbers a1 all the way up till ak, right. So, this is the sum of these. In fact, we can simplify. So, what are we looking for? We are looking for the coefficient of x raised to n, right, in this expression. In this generating function, we are interested in the coefficient of x raised to n, right. But x raised to k is always there. Okay, so you know that the coefficient of x raised to n, there is an x raised to k here. So, the really interesting part is a coefficient of x raised to n k minus n in this series, right, x raised to k minus n. If you find the coefficient of x raised to k minus n in this ratio, then you just have to multiply by x raised to get the coefficient of x raised to n in what you are interested in, right. What we are interested in this coefficient of x raised to n, there is always a factor of x raised to k there, right. So, if we understand this series, the expression for this ratio, the coefficient of n minus k there, sorry, n minus k, then you will have your answer for the Stirling number, right, because x raised to k is always sitting there, right. So, what is this saying? Coefficient of x raised to n in sk, this is what we are interested in, right. But sk is what? Sk is x raised to k times 1 upon this. So, this is the same as in right. So, if we can find the coefficient of n minus k in this, then that will be equal to the coefficient of x raised to n in this, right, because sk is just x raised to k times this quantity, right. It shifted, just shifted. Okay. This x raised to k here, this is not going to change the coefficient, right. Multiplying by powers of x only just shifts your sequence. Okay, maybe I will stop here and continue after lunch.
AK is k factorial 1 by
It's much more involved than that. It has factorials, but it's much uglier than that. So, yeah, so that's why I'm stopping before lunch. Otherwise, you will eat me. Okay, so let's continue after lunch. You will be sleepy. I'll do the derivation quickly, and we'll be done with that. Yeah.